Alright, so this is a new playlist, Generative AI, and you can use Generative AI for synthetic data generation, for domain adaptation, for contrastive learning, and many applications. But in this lecture, I'm going to be focusing on this paper, Generative Adversarial Networks, this paper in 2014, which is very important and has huge citations for many reasons. So we propose a new framework for estimating generative models via an adversarial process in which we simultaneously train two models. A generative model that captures the data distribution, and a discriminative model that estimates the probability that the sample came from the training data rather than G. Because your training data, for example, could be real images, but G is generating synthetic images, so there is a war going on. So it is a game between two of them. And so the training procedure for G is to maximize the probability of D making a mistake. So we say we fool D. G tries to fool D. And this framework corresponds, so it's a minimax two-player game. Because the space of your generator and D is huge, a unique solution exists with G recovering the data distribution and D equal to D. So in the case where G and D are defined by multi-layer perceptrons, the entire system can be trained with backpropagation. The interesting thing is that there is no Markov chain. Because it's a generative model, there is no Markov chain. So in the proposed adversarial network framework, the generative model is pitted against an adversary, a discriminative model that learns to determine whether a sample is from the model distribution or the data distribution. Because the model distribution, for example, tries to synthetically generate an image, but your data distribution, for example, could be real images that is already there. So the generative model can be thought of as analogous to a team of counterfeiters trying to produce fake currency and use it without detection, while the discriminative model is analogous to the police trying to detect the counterfeit currency. Competition in this game drives both teams to improve their methods until the counterfeits are indistinguishable from genuine articles. So this framework can yield specific training algorithm for many kinds of model and optimization algorithms. So we explored a special case when the generative model generates samples by passing random noise through a multi-layer perceptron. And the discriminative model is also a multi-layer perceptron. But nowadays, any kind of network can be discriminative or generative. So it's a framework. And they refer to this as an adversarial network. So we can train both the models using only highly successful backpropagation and dropout algorithm, and sample from the generative model using only forward propagation. The adversarial model is most straightforward to apply when the models are both multi-layer perceptron. To learn generative distribution over data X, we define a prior and the input noise variable. Then represent a mapping of data as G, where G is a differentiable function represented by a multi-layer perceptron with parameter theta sub G. We also define a second multi-layer perceptron. So this one is discriminator and outputs a single scalar. D just represents probability that X coming from data rather than your probability distribution of generator. So we train D to maximize the probability of assigning the correct label to both training examples and samples from G. We simultaneously train G to minimize log of 1 minus discriminator of generator of your sample Z. In other words, discriminator and generator play the following two-player minimax game. This is the value function, V. V is value. What is the value if I have a kind of discriminative and a specific generator? So first we can maximize D, just train for D, then we fix it. You can fix it, then you go to maximize G, but it's a loop, and they are coupled together, and you will see why you need to train G less than D. I mean, the speed of them is very critical, otherwise you cannot have a good GAN model. So you see the speed of training is very critical. Very critical. You want to G, because we know the final solution. We know the optimal solution convergence is P of data divided by P of data plus G. So it's very important to tune the speed of generator with the speed of discriminator, because they are not the same. So that's why we have K steps for discriminator, but just one step for generator. Of course, there is a loop and it carries on until convergence. But you should pay attention to this one, that this is just updating using stochastic. It's updating your discriminator, and the next one we updates the generator. So we know the global optimality, and we can prove easily that this is the optimum. And so there is a theorem that says the global minimum of the virtual training criterion is achieved if and only if P of generator is equal to P of data. At that point, C of G achieves the value log 4. So this proposition says that this one then converges to P of G converges to P of data. For example, you see visualization. The rightmost column shows the nearest training examples of the neighboring sample. In order to demonstrate that the model has not memorized training set, samples are fair random draws, not cherry-picked. Unlike most other visualization of deep generative models, these images show actual samples from model distribution, not conditional, means a given sample of hidden units. And so this is the digits obtained by linearly interpolating between coordinates in Z. And this is the challenge in generative modeling, because it's a summary of difficulties encountered by different approaches to deep generative modeling. For example, adversarial models, which is of interest, for sampling, there is no difficulty for sampling. But for inference, they have learned approximate inference. For model design, any differential function is theoretically permitted. These are challenges. I mean, the space is huge. And also not explicitly represented may be approximated with parse and density estimation. Also, synchronizing the discriminator with the generator is a problem. So you should, as I said, K of discriminator, 1 for generator. So there is a trick for that as well. So it's very tricky. But the pros and cons. This new framework comes with advantage and disadvantage. The disadvantage is primarily there is no explicit representation of your generator, and that D must be synchronized as well with G during training. So adversarial models may also gain statistical advantage from the generative network not being updated directly with data example, but only with gradients flowing through their discriminator. This means that components of the input are not copied directly into generative parameters. Another advantage of adversarial network is that they can represent very sharp, very degenerate distributions, while methods based on Markov chain require the distribution be somewhat blurry in order for the chain to be able to mix between modes. So in the next lecture, I will explain this conditional generative model, because we can condition on some, for example, label, class, or feature, or anything. And it has many advantages. And also one can approximately model all conditionals. But S here is a subset of indices of X by training a family of conditional models. Also, semi-supervised learning features from discriminator or inference could improve performance of classifiers when limited data is available. Also, efficiency improvements training could be accelerated greatly by devising better methods for coordinating G and D, or determining better distribution to sample Z from during training.